Okay, welcome. This is the geometry final review for the spring semester of 2019. Looks like there are 7 people so far, and I'll kind of stall a little bit and talk about how this is going to work and how it goes, and we'll see if a few people join us in the next minute or two, and then we'll get started on the math. I had the few thoughts about what we should cover. I was thinking I would go over the previous tests that we've already had that kind of covered the critical material. So test 3, which was on the 3rd unit on trigonometry, then test 4, which was on the 4th unit on circles, and then quiz 9, which is on our most recent unit on solids. I'll probably emphasize the core standards, but if people ask questions about the extended standards, I'm happy to go over those as well. I'm going to do math from 7:30 to 9. If we go over all of those tests and we still have more time, I'll probably look at some of the semester review worksheet that I gave you last week. If at any point you have any questions or comments or want to know how I did something or think I need to slow down or there's an issue, you should join in on the live chat on the side. I can see that there's 5 people watching. It'd be great if you checked in just so I know that you can hear me and you can see me and everything's working well. And that you're actually able to use the chat and everything. I know Uriel can, because Uriel came to the pre-calc review last night. And at least a few of you are able to hear me and see me. It's unclear whether everyone can, but okay, good. Looks like most of you are capable. Sweet. Jonathan can hear me. Excellent. Oh, Larry, of course. Great, Larry, clearly. Look, we've got about a few people here in the live. So since you're here in the live session, you can, participate, make comments, get extra help. If I need to go over something in more detail or something that you in particular want to hear, then this is all for you. So, join in on the chat and let me know what you want. And then, of course, this whole session is recorded and is available afterwards. So people who weren't here can watch it later. Or if you want to watch something again, you're certainly welcome to. Okay. If there are no questions about how this works or what's happening, I'm going to go ahead and start doing math. Exactly 3 minutes in. So this was our 3rd quarter test. It went over our 3rd unit, which was on similarity, right triangles, and trigonometry. This is question 1 from this 3rd quarter test, which was on a core standard that given 2 figures, you should be able to use the definition of similarity in terms of similarity transformations to decide if the 2 figures are similar. So 2 figures are similar if and only if I can get from one to the other using rotations, reflections, translations, and or dilations. So I need to state a sequence of transformations by which I could get from here to there. So I generally like to begin with translation. So I'm going to start with a translation. I'm going to make a copy of this figure that I can translate. And I'm going to map ABCD onto G8, EFGH. If you brought EFGH to ABCD, that would be fine. But I'm going to go from small to big. So there's my copy, just like you would make a copy with patty paper. And I'm going to translate. I can see that it looks like point D should map to point H. So I'm going to say, first step, map D to H. Step 1, translate by a vector that maps D to H. Cool. Now, just so we can see all of my steps, I'm going to leave that one there in blue. and make a second copy. And then I'm going to go ahead and rotate. So I want to rotate it so that another pair of corresponding points lines up. So I can see that that the side DA should rotate to map up with HE. So I'm going to rotate by 90 degrees. So now I'm over there. So on step 2, I've now rotated about point H by, well, it was a 90-degree angle, I can see that, but I'm going to go ahead and name the angle. This was A prime, and I mapped it to E, so by angle A prime H E. Cool. Now there's going to be a third step. So I'm going to switch to a green color. And it looks like we clearly need a reflection. So I'm going to have my third step go ahead and be a reflection. So I'm reflecting up there, and then this is going to reflect up to there. Let's see. That was over. So right there. And right there. So there in green is my third step. And in my third step, I'm going to say that I reflected over HE. Cool. And then I'm going to have one last step. I'm going to do my last step in purple. And I obviously need to dilate if I'm going to map ABCD to EFGH. So the last step, step 4, is dilate about H. And I can count, so I can see that this was 4 and it became 5, 6, 7, 8, 9, 10. So if I want to multiply 4 and get to 10, I would need to multiply by a factor of 2.5. But even if I couldn't count, I could just say dilate about H by the factor that would map, let's see, this was H. Let me finish my labeling here. I had A prime, B prime, C prime, D prime in the blue one. Then I made the red one, and it was D prime was still there. So D double prime. In the red one, after D, there was A double prime. So then this one here is A triple prime and B triple prime, and this is C triple prime and D triple prime. Okay, so about H by the factor that would multiply and let me get from AD to EH. There we go. Okay, and then Mini Break has an excellent question. How would you write it if you wanted to get a 4? What would it look like as a 4-pointer? Which is a great question. So I have already stated my entire set of transformations in terms of the given points. So I didn't use any numbers. I didn't use any made up lines that I added in there, like line L or line M. I didn't use any angles that I made up. I did everything in terms of A, B, C, D, E, F, G, and H. So that's one of the things that needs to happen to get a 4. The second thing that would need to happen to get a 4 is I would have to write it using the function composition notation. So in that case, I want to say that figure EFGH is the result of a set of 4 transformations. The last one was the dilation about H by the ratio that mapped AD to EH. Then that was the dilation of what I got when I reflected over line HE. And that was the reflection of what I got when I rotated about H by angle A prime HE. And that was the rotation of what I got when I translated by vector DH. And what did I translate? I translated the original figure ABCD. So this is what your answer would look like if you were trying to score a 4. Oh, and that was Jesus's question. Great question, Jesus. Hopefully I've answered it. That look good, Jesus? Hopefully. Anyway, I would say that that's a pretty clear standard. Can you, given 2 figures, use the definition of similarity in terms of similarity transformations to decide if they're similar? That's going to look pretty much like that. There will be 2 figures. You'll have to write transformations to decide if they're similar. Cool. That's number 1. Unless there are any questions back on number 1, I'll move on to number 2. Number 2, which is another core standard from our 3rd unit on trigonometry. This core standard said use trig ratios and the Pythagorean theorem to solve right triangles in applied problems. Oh, Destiny has a question. Is the final going to look like our test that we have in class? Yes. Our final is going to look like our tests that we have in class. Very similar, just a tad longer because it's the whole semester and all. Okay, let me get rid of what I had up there so I can read. Mr. Williams has a 20-foot ladder. So let's draw in Mr. Williams's 20-foot ladder. So this is the ladder. And it's 20 feet. Okay. Safety recommendations indicate that the ladder should be placed at a 75-degree angle with the ground. So here's the ground. And how tall will the top of the ladder be at this angle? So here's the wall. And there's a 75-degree angle. And I would like to know, how tall is this distance up the wall? How far up the wall can I reach if I use a 75-degree angle with my 20-foot ladder? So this is opposite from the 75, and this is the hypotenuse. So since I'm dealing with opposites and hypotenuses, I clearly want to make use of the sine ratio. So I'm going to draw a little tiny right triangle and say if this was 75 and this was 75 degrees is in there, then this would be the sine of 75. So that sine of 75 over 1 should be the same ratio as our height up the wall, x, over 20, which means that x equals 20 times the sine of 75. Because in order to get x by itself, I'm going to times by 20 and times by 20, and those will cancel. So if x equals 20 times the sine of 75, I'm going to plug that into a calculator. And here's the calculator I actually have on my iPad. It's going to be 20 times the sine of 75 degrees, which makes 19.32 feet. Cool. Alrighty. The next question says, though 75 degrees is optimal, anywhere between 70 degrees and 80 degrees is within the safety recommendations. If Mr. Williams places the ladder 3 feet from the wall that he's working on, is it safe to go up? So again, I still have the same 20-foot ladder, 20 foot, but now I'm placing it 3 feet on the ground. 3 feet. And our question is it safe to go up? So, what is that angle? And now I know the adjacent side and I know the hypotenuse, and I'm wondering about the angle. So if I need to write a ratio involving the adjacent and the hypotenuse, then clearly I want to make use of the cosine ratio. Cosine is for adjacents and hypotenuses. So the cosine of my angle is going to be equal to the adjacent side 3 divided by the hypotenuse 20. So let's see. My angle equals the inverse cosine of 3/20. And I'm going to pop that into a calculator. Inverse cosine of 3/20, 81.4 degrees. So the angle between the ground and the ladder would equal 81.4 degrees. So the answer is no. 3 feet from the wall is not safe. It is outside the recommended safety guidelines. Cool. And here I was 19.3 feet up the wall. So that was number 2, the core standard from our 3rd unit on trigonometry, similarity, and right triangles was use trigonometric ratios in the Pythagorean theorem to solve right triangles in applied problems. So you're pretty much guaranteed that you're going to have a word problem, and you'll need to use trig and maybe also the Pythagorean theorem. Any questions on number 2? Okay. Number 3. My math font isn't coming out exactly right, but looks okay. Dilate triangle ABC about point D by a factor of 2. So that means all of the points are going to get twice as far away from point D as they were before. So here was the distance from D to A. And we're going to double that distance down to there. So there's my new point, A prime. And here's the distance from D to C. And we're going to, oh, whoops, messed that up. So again, there we go. And okay, here's the distance from D to C. And we are going to double that distance. So doubled down to there. C prime. And then we're going to take the distance from D to B. And D to B. That's like that. And double it. So that takes me to there. Cool. So now I have A prime, B prime, C prime. So my new triangle is going to look like that and like that and like that. Okay. And we need to find the tangent of angle A and the tangent of angle A prime. So here's angle A. The tangent ratio is the opposite over the adjacent. Here's the opposite. It equals 3. Here's the adjacent to angle A. Equals 1, 2, 3, 4, 5. And then down here for A prime, here's the opposite of angle A prime. It equals 6. And the adjacent to angle A prime, it equals 10. So I can write that the tangent of A equals 3 over 5. And the tangent of A prime equals 6 over 10, which reduces to 3 over 5, which is 0.6. Okay. And then the last part asks me to explain why the tangent of angle A is equal to the tangent of angle A prime. Okay. So I'm going to write that we had some properties of dilations, and one of our properties of dilation says that when I dilate about point D, all the lengths of triangle ABC grow by the same ratio. 2. Since a since tangent is the ratio between two sides, it remains unchanged. The ratios between the sides are the same after a dilation. Um, I often have people tell me about how angle A doesn't change. Angle A is the same as angle A prime. That's cool and is certainly true, and I like that. But it doesn't, the thing that is crucial here is that you know that tangent is not really, is only by extension about the angle, that tangent is primarily about the sides, but because the dilation doesn't change the side ratio, it then stays the same for any angle A in any right triangle with that angle A. So you want to tell me something about dilations and the ratios between the sides of triangles. That's the crucial concept on that standard, right? The standard is really clear that you understand that because of similarity and dilations, side ratios in right triangles are properties of the angles. But that's why you're able to define trig ratios. So again, you're likely to have a question fairly similar to that one on the final exam, where you're able to explain why it is that dilations and similarity allow us to define the trig ratios. What is a trig ratio, and why can we say that the tangent of angle A is always the same in any triangle with angle A? That's what you need to be able to explain. Are there any questions on that one? Number 3 from the third test. Seeing no questions, I think I'm going to skip past the extended third-quarter test and jump to 4 on circles because I want to emphasize the core standards if there aren't any questions on the extended. If you have a question on an extended standard, please let me know and I can go backwards. But let's look at the core standards primarily because many people need to meet the core standards this week. Okay, so here I'm looking at test 4, which is on our 4th unit on circles, which was in the first half of the 4th quarter. So test 3 was after the 3rd quarter. Now I'm looking at the first thing we did in this quarter, the 4th quarter. And the first core standard on circles is that you be able to identify and describe relationships between inscribed angles, radii, and chords. So here I'm using the inscribed angle theorem, which says that if I know that this angle intercepts this arc, so there's an angle and it's intercepting, let's see, let's make a kind of a pink arc. I don't have any pink color. Let's do a new kind of pinkish color. So this purple angle intercepts this kind of pink arc. And then I have another inscribed angle, which is this green angle, and it intercepts this kind of light green arc. That one there. And then I should be able to see that all together, arc RST goes all the way around there. So that's 180 degrees. So my pink arc here plus my light green arc here is going to be 180 degrees. So if I've got 59 degrees there, I need to use my inscribed angle theorem, which says this angle is 1/2 this arc. So if I double the angle, I can find that arc. So I'll double 59 degrees, and that's 118 degrees. 118 degrees. And now I can say I knew that arc RST altogether was 180 degrees. So I can say 118 degrees in order to get to 180 degrees. Well, I must have had 62 degrees right here. And now that I know this arc that my green angle intercepts, if this is 62 degrees, then my green angle must be 31 degrees. 31 degrees. So there's the answer, 31 degrees. Then number 2, I got 85 degrees and 70 degrees, and I need to use my theorem that says if I have this angle A and this arc B and this arc C, that I can use my theorem that says angle A equals the sum of B plus C over 2. So that means angle A, which I know to be 70 degrees, is equal to arc B, 85 degrees, plus arc C, which I'd like to know, over 2. So that means that 140 degrees must equal 85 degrees plus C, because 140 divided by 2 would equal 70. And that means, well, let's see, what do I need to add to 85 to get to 140? Well, 55. Angle C equals 55 degrees. So here, sorry, not angle. Arc C is equal to 55 degrees. And then on this one, number 3, I've got a question that asks me to find the length x here, and I need to use another theorem that says when two chords cross in a circle, that their product, the product of their portions should be the same. So I can say that, well, let's write out our theorem. We said, I think on this one it was A, E, B, C, E, D, and then the theorem reads A, E times E, B, the product of those two portions, is equal to C, E times E, D. So A here is X times EB is 12, and that's equal to CE is 14 times ED is 6. So 12x equals 6 times 14. Let's see, that's 60 plus 24. I think that's 84. And then if I divide by 12, x equals 84. I'm thinking that's 7. 7 times 12 would be 70, 84. X equals 7. Great. Cool. Then the last practice problem here, number 4. Again, need to look in my test notebook for the theorem that's relevant. And it looks like this. A, B, C, D. And it tells me that AB squared equals AC times AD. And AB is 18. A to C is 12. And A to D is just X. So A all the way to D is the 12 plus X. So 18 squared, oh man, I'm gonna need to go to my calculator for that one. 18 squared is 324. And then 12 times 12 is 144. And 12 times x is 12x. And then I'm going to minus 144 on both sides. And oh, I like to notate my canceling like that. So 324 minus 144 leaves me with 180 degrees. No, not degrees. Sorry, just 180. Equals 12x. So that when I divide by 12 and divide by 12, I'm at x equals 15. Cool. So that's kind of questions you're likely to see that assess whether you are able to identify and describe relationships among inscribed angles, like these inscribed angles, radii, and chords, like these chords. That's the first question from the circles test. Second question from the circles test. Well, this is the same core standard, but it's just an applied problem. Probably won't get an applied problem on the final exam. I think the theorem here says that if you've got A, B, C, D, E, then A. Oh no, sorry. I'm looking at the lengths one. We need the arcs and angles one. The theorem here says that if you have an angle A and an arc B and another arc C, that A equals B minus C over 2. So in this case, A equals 60 minus 30 over 2. So A equals 30 over 2. So A equals 15 degrees. That's number 2. Probably not likely to see a word problem for that standard on the final exam. Hopefully I'm not going too fast. We've covered a lot and I haven't gotten any new questions, but I do see 12 people watching. Hopefully you're all able to still see and hear and are just understanding everything. That's the goal. The next core standard and the second core standard for circles says find arc lengths and areas of sectors of circles. So we have a formula for that. You just have to use the formula. I think this is a pretty straightforward standard. Mostly you guys do pretty well with this standard. So here the formula for the length of an arc is that the arc length, I'll call it A, is equal to the circumference 2 pi r times the angle theta all over 360 degrees. So that means I've got 2 times pi times 19 times 240 degrees all over 360 degrees. And this is another standard where there's multiple ways of scoring. If I just plug that into a calculator directly, I just type everything in exactly the way I see it, then I'm going to get an approximate answer, and that could score you a 3. But if you are able to write the precise answer, you could get a 4. So here, the approximate answer is 79.6. I don't. Do you mind not doing it tonight? I'll take care of it. I don't worry about it. Okay. Sorry, I'm gonna be a little bit late. Okay. Apologize. Okay. Thank you. Apologize for the interruption. 79.6 miles. And then the even better answer would be the precise answer. So there I'm going to write it and not approximate pi. So I'm going to leave pi out of my calculation. And it's going to be 76 pi over 3 miles. Cool. That's the first one. Well, let me zoom in there a little. Then the second one, let's give ourselves a little more space. Cool. So on the second one, we've got the same formula. A equals 2 pi r times theta all over 360 degrees. And in this case, A equals 2 pi times 9 times 315 degrees over 360 degrees. This was the approximate answer, approximately, and this was the precise answer. So here, if I first got a 3 and I just typed everything into the calculator exactly as I saw it, 2 pi times 9 times 315 divide by 360, I would get 49.48. So A is approximately 49.48. But then if I got a precise answer, I do 2 times 9 times 315 over 360. And that would be 63 pi over 4. And these are both in kilometers. Kilometers. A dodecahedron made of concrete. Cool. That's a great looking shape. If you drop a nice small dodecahedron made of concrete on yourself, then it won't be so bad. But a large dodecahedron made of concrete could be somewhat miserable. Let's see. Then number 3 and number 4 are both asking about the sector area formula. So here I'm going to write sector area with an S. And the sector area formula says use pi r squared times the angle over 360. And that means I've got pi times 13 squared times 270 degrees over 360, which is approximately 398.2. Approximately 398.2 centimeters squared. And then if I did it precisely, I'd have 13 squared times 270 over 360, which is 507 pi over 4 centimeters squared. And that's precise. Okay. And same formula for number 4. I'm going to do pi times 12 squared times 150 over 360, which is approximately 188.5 kilometers squared. And then it's exactly 60 pi kilometers squared. So S is exactly equal to 60 pi square kilometers. Cool. Generally, students do pretty well on this standard. If there aren't any questions, I'll go ahead and move on. Let's see. I love this question. This is a great question. At Pie Time Pie Shop in Circleville, the pie is cut into slices with a 25-degree angle. So let's draw a picture of a piece of pizza. Pizza. And it's got a little crust happening in here. And then I like my pizza with pepperonis on it. So this one has some pepperonis on it. And then, of course, it has a 25-degree central angle, except the pepperoni kind of got in the way of the angle. So 25-degree angle. This Tuesday, there is a special promotional offer, and customers have the option of either doubling the angle of the pie size to 50 degrees. So let's see, what would it look like to double the angle of the pie slice to 50 degrees? So if I double, let's make two, oh, whoopsie. Let's say here, group, and then double, duplicate, and here's doubling the angle. And it's going to look like that with a double angle. So that's what it looks like if you get double angle pie slice. So now you've got a big pizza with twice the angle. It went from 25 degrees in each slice to now a total of 50 degrees. So this is double angle. And then your other option is you could go to double the radius. So let's get another copy here and look at what doubling the radius does for you. So if I double the radius, I'm going to get a pizza pie that looks like that, where my radius is now twice as long. Cool. So that looks like twice the length of the radius. So that's double radius. Okay. So which gives you, or does one option give you more pie than the other? Or are they the same? How do you know? Explain your reasoning. Oh, I guess I never said anything about pizza. Maybe it's like cherry pie or something. Anyway, um, let's see. Pretty clearly, I'm thinking this double radius game here looks pretty bummer. So this looks like it's better than that, just kind of offhand. But let's kind of do some work here. What a lot of students did successfully was they said, let me make up a radius and find out. So they just kind of said something like, let's pretend, it doesn't tell me anything about a radius, but let's pretend that the radius equals 10 inches. So then in double angle, so the original pi would then be a sector area of pi times 10 squared times 25 degrees all over 360. So the original amount of pi would have been 21.8 inches squared. And then if you double angle, you're going to have pi times 10 squared times 50 degrees over 360 degrees, which gives you 43.63 inches squared. And then if you double radius, you're going to have pi times 20 squared times only 25 degrees, because you didn't double the angle, over 360, which gives you 87.27 square inches. Oh, man. That's got to be the best deal. So we should have said something here like, let me see, let me move all of my other work out of the way. Oh, okay, that was important. Those were important. Oh, okay. So here's my diagram. And out of the way. So we should have said double the radius gives you twice as much pi as double the angle. And if you then wanted to explain the reasoning, a really awesome answer would have said something about when you double the radius, the area quadruples. Because it increases by 2 squared equals 4. When you double the angle, you just get twice as much area. So with doubling the radius, you've dilated the pizza pie by 2. So we're talking about areas of similar figures, and the radius increases by the dilation factor squared. So 2 squared is 4. You get quadruple the amount of pizza. When you go here and just rotate, you only get double the angle, so only twice as much pizza. So this is actually twice as much pizza as this. So definitely go with double radius. We got a little comment from Jesus on how appetizing my pie looked. So maybe he's left us now to go get pie. It's possible. But if there are no other questions on number 4, I'll go ahead and look at the most recent standards. The last 2 core standards are from our most recent unit on solids. This is now unit 5 on solids. And there are 2 more core standards. Okay, that's extended. That's extended. Extended. Again, if there are questions about the extended standards, I'm happy to go over them. But let's talk about core standards for solids. So here's Carlos and the well. So Carlos is using cylindrical buckets. So here's a bucket. It looks like this. You get them. Mine are all from Home Depot, so they're orange. Maybe you have some that look the same. This is a classic 5-gallon bucket. It's 15 inches high, and it is 12 inches in diameter. So mine's a little tall for scale. That's better. So it looks like that. Okay. So Carlos is using buckets like this, and he's going to put all of the buckets in a truck. He's going to fill up a bunch of buckets with water, and then he's going to take all these buckets of water and put them in a big supply container, which is 3 feet wide and 6 feet long. So it looks like that. Container. So emergency water up on the hill for the fire department to use. And let's see, a little discussion going on in the comments here. I think, oh, I forgot who Mini Break. Oh, Mini Break is Jesus. Who's Papyrus the cool guy? I don't know. Mini Break asks, will the final be going over the stuff we learned in the 4th quarter? And then, so that was Jesus. And then Papyrus the cool guy responded. So that's not Jesus. Papyrus the cool guy is me. Thanks. Papyrus the cool guy. Oh, Eric said that yes, the answer is we're going over the final exam is everything we went over in the entire semester. So that's 3rd quarter and 4th quarter. 3rd quarter trigonometry, 4th quarter circles and solids. Thank you, Eric. Well said. Okay, so the question is, how many buckets do I need to fill up this whole emergency water container? So I'm going to find the volume of a bucket. Volume here of a cylinder is the area of the base, pi r squared, times the height. So that's going to be pi times 12. Well, I'm going to work in feet. 12 inches is 1 foot times a height of 1.25 feet. Because 15 inches is 1 foot 3 inches. 3 inches is a quarter of a foot, 1.25 feet. So I'm looking at just 1.25 pi, which I can approximate. And when I approximate 1.25 pi, I get 3.9 square feet. It's about 3.9 square feet. Okay, then how many square feet are in this emergency water bucket? Well, it looks like it's 6 by 3 by 3, which is 54. Oh, I made a mistake back here, though. Good. Okay, so 54 cubic feet in my emergency water container, but I made a mistake back here. The radius was not 1 foot. The radius should only be half a foot. The diameter is 1 foot. The radius is only a half squared. So it's not as easy as I remember to do it in feet. Probably to be just as easy to do in inches. But the crucial thing that a lot of people messed up on this was not thinking about the difference between feet and inches. So we had zero point 0.5 squared times 1.25 times pi. So one bucket is actually only 0.9. So volume for the bucket is only about 0.98 cubic feet. And then the question is saying, how many buckets do I need to use to fill up the emergency water container? Well, I'm going to do 54 divided by that 0.98, and I get 55 buckets. 55 buckets to fill container. Okay. So this is one core standard. Are you able to use volume formulas for cylinders, pyramids, cones, and spheres to solve problems? And then your last core standard for this semester was on scale solids. So thinking about length, area, and volume measures when we dilate solids and make them similar figures. So 1 and 2 said, if they're similar, find the ratio of the volumes. So here, the scale factor looks to be 72 to 32. 72 to 32, which reduces to 2 1/4. So 9 to 4. And then the volume is, remember this is A to B, and volume ratio, there we go, is then going to be A cubed to B cubed. A cubed to B cubed. If figures are similar, then the ratio of their lengths cubed is the ratio of their volumes. So 9 cubed to 4 cubed, we're talking about 729 to 64. Okay, so I just took these and cubed them. 9 to the third power was 729. 4 to the third power was 64. Same deal in the second question on surface area. I've got 425 to 1088. 1088. Which is 25 to 64. So the scale factor is 25 to 64. Oh, sorry, that's not the scale factor. This time they did not give me the scale factor. They gave me the surface area ratio. And so the scale factor, I don't know yet. It's going to be A to B. Then I know the area ratio. It's going to be A squared to B squared, and I have to get the volume ratio, which is going to be A cubed to B cubed. And before I proceed, see someone's asked a question. I don't know who Lizard is, but they're asking, are you just going over core standards or are you also going to go over extended? So I have so far only gone over core standard, but I'm reaching the end of the core standards and I still have about 20 minutes left. So I'm happy to go over any extended standards questions if people would like me to. So 25 to 64 was what I got right here. This was the ratio of the surface areas that they told me. So now I need to square root that. To get 5/8, which is the scale factor. And then I'll need to cube 5/8 to get the volume ratio, 125 to 512. So to get here, I square rooted. And then to get here, I had to cube. Okay. Third question, same idea. I've got the ratio of the areas, and I need to find the ratio of the volume so I can find the volume of a second solid if there are two similar solids. So I know, again, that the scale factor will be some ratio A to B. The area ratio will be some ratio A squared to B squared. And the volume ratio will be A cubed to B cubed. So, I don't know why Larry is shout texting Eric's name. Not sure there. Let's see. I know surface area is what's given, 396 to 1100. So this equals 396 to 1100, which I believe reduces 396 to 1100 is 9 to 25. So I can square root that to find the scale factor. And that's 3/5. And then I can cube my scale factor to the third power to get the volume ratio, which is therefore 27 to 125. So now that I have the volume ratio, I can multiply by the volume ratio to get the new volume. So if there's some small volume of 4,752, when I multiply by 125/27ths, I will get the larger volume. So 4752 times 125/27ths gives me a larger volume of 22,000 cubic meters. Cool. And the last one, make a little more space. I've got, again, the same deal. The scale factors will be in some ratio A to B. The area will then be the scale factor squared, and the volume ratio will be the scale factor cubed. So I know the volume ratio. It's given. It's going to be 15309 to 21. 15309 to 21 is the same as 729 to 1. I need to take the cubed root of that to get the scale factor, which is 9. And then I'm going to square the scale factor to find the area ratio. So that's going to be 81 to 1. So now when I multiply the surface area of the small one by the area ratio, so that'll be times 81 to 1, I'll get the area of the larger surface area. So 1458 times 81 equals, oh, sorry, divide by 81. The solid number 2 is clearly smaller, times 1/81th. My bad. 1/81th. So 1458 times 1 divided by 81 equals 18 yards squared. Cool. So here we had this. We square rooted to get that. And then we cubed to get that. Here we were given volume. We cube rooted to get the scale factor, and then we squared to get the area ratio. Uh, let's see. Govna. Hello, Govna. I think that's allowed. I had to review that. YouTube apparently thought that might be inappropriate, but Govna seems okay. Hello, Govna. Anyway, number 2. That's it. Any questions? That is the last core standard. I could finish this test. There were more questions on it about Jesse. And so this was a core standard question, so I'll probably go over that. Lizard, if you have any urgent questions about extended standards, now is the time to ask them. We have about 15 more minutes, and I'd be happy to go over extended standards, but I will probably not be able to cover all of them. So you were the only one who asked about extended standards. If you have one you want me to go over, now is the time to ask. So this last one, number 3, should have been super easy. Jesse wanted to make a shoebox that would hold 100 pairs of shoes. Nathan said, if you make it 100 times bigger, Then you'll multiply the length by 3,500 to make the 3,500 centimeters. You should have realized immediately Nathan is wrong. If you multiply length, width, and height by 100, the volume, I can't spell volume, volume will be, see, 100 times 100, that would be 100 times 100 is 10,000 times another 100 is, let's see, 1, 2, 3, 4, 1,000,000 times bigger. Will be 1,000,000 times larger. Jesse only needs 100 spaces, not 1,000,000. That would be an excessive amount of shoes. So Jesse could just make the box 5 times bigger. Five times 5 times 5 equals 125. So plenty of space. So the key issue is you had to realize that if you want to fit in 100 shoes and your friend says, oh, you should just make that box 100 times bigger, they're clearly wrong and they don't understand how volume relates to length. If you make the shoebox 100 times longer, 100 times taller, and 100 times wider, that would be way too big. And rather than just fitting 100 shoes, you'd fit 1,000,000 shoes in your box. 1,000,000 shoes is too many shoes. So we do have about 12 more minutes. I've gone over all of the core standards questions I intended to. I'm happy to start going over extended standards. Since I have 12 more minutes, I'll probably just go back to the beginning and start with the extended standards from the trigonometry stuff. But if anyone wanted to hear any particular extended standards on circles or solids, you should probably ask, because I will clearly not have enough time to go over all the extended standards questions in the next 11 minutes. But seeing no questions, I'll start talking extended. Or are there any core standards questions that I missed that anyone needed, or that I went too fast over that you guys want to see again? Or were there any core standards questions on the semester review that anyone didn't know how to do and wanted me to go over? I'd be happy to do either of those things as well. But you'd have to ask. Seeing no comments, I'll go ahead and go back to our third quarter which was on trigonometry, similarity, and right triangles, and start looking at some of the extended standards. You need to meet the core standards to pass the course, get a C. If you meet the core standards and also meet some of the extended standards, you'd get a B. If you meet the core standards and meet all the extended standards as well, that would be an A. So here was one extended standard from third quarter, angle-angle similarity, but not angle-angle-angle similarity. And that's because if you know two pairs of angles in a triangle are congruent, then the third pair must be congruent because the sum of the interior angles of a triangle is always 180 degrees. So there'd be no need to look for 3 pairs of congruent angles. As soon as you'd found 2 pairs of congruent angles, you'd be set, which was why it's the angle-angle similarity theorem and not the angle-angle-angle similarity theorem. Number 4, are the following triangles congruent, similar, or none of the above? So let's see. Here, 4, if I times 3 by 4, I would get 12. If I times 4 by 4, I would get 16. If I times this 2 by 4, I would get 8. So this is clearly similar. By side, side, side. Scale factor is 4. And here, those are not similar, not congruent. We don't know anything about those. All we know is that there's one pair of congruent angles, but we can in fact say that they are neither similar nor congruent, definitively. And here we can say congruent by side angle side. And in the last one, we can say similar by angle angle. Okay. Any questions on number 5 from our third quarter exam on similarity, right triangles, and trigonometry? On number 6. Ooh, I love this one. There's a triangle ABC. A, B, C, A, B, C, and dilated about point A by a factor of 2, which means every point gets closer Oh, about point A by a factor of 2. So that means it's got to double. So should have made it a little smaller. Let's go ahead and shrink it down. And then dilate by a factor of 2. Duplicate. And double. That looks reasonably well doubled. Yeah, a little bit larger. Okay, so there's B prime, and there's C prime, and A prime. Cool. Use the diagram to show that the segment connecting the midpoints of two sides of a triangle is half as long as and parallel to the third side. So here's the segment that connects this midpoint and this midpoint. So it would say BC connects the midpoints of A prime B prime and A prime C prime. It is parallel to B prime C prime because dilations map lines to parallel lines. It is half as long as B prime C prime because the factor of dilation was 2. Dope. That's it on number 6. Number 7. Ooh, another one of my favorites. Why is it that the sine of 32 is equal to the cosine of 58? Well, if I draw another right triangle, here's going to be 58 degrees, and there's going to be 32 degrees, and there's 90 degrees, and I'm going to name this side A, and this side B, and this side C. So the sine of 32 equals the opposite A over the hypotenuse C. And the cosine of 58 is equal to, well, that's the adjacent A over the hypotenuse C. So sine of 32 equals the cosine of 58 because the opposite of 32 degrees is always adjacent to 58 degrees. Ooh. And that was great timing. I think I'll do one last problem, and then that's our session. It'll be 9 o'clock. sketch and label a 30, 60, 90-degree triangle. There's one like that with a 60 degrees and a 30 degrees. The side ratios are always in the ratio of 1 to root 3 to 2, so that the sine of 30 degrees is going to be opposite over hypotenuse 1/2. The cosine of 30 degrees is always going to be adjacent over hypotenuse. And the tangent of 30 degrees is always going to be opposite over adjacent, 1 over root 3, which when I get the radical out of the denominator is root 3 over 3. And then the sine of 60 degrees is opposite over hypotenuse root 3 over 2. The cosine of 60 degrees is adjacent over hypotenuse 1/2. And the tangent of 60 degrees is opposite over adjacent root 3. There it is. That is the end of our second semester final review. If there are no last remaining questions, I'll just say good luck tomorrow. And I hope this was helpful. Good night, all.